When you're doing a point estimate for lambda, the most likely thing you're doing is working on coming up with an estimate for an exponential distribution, which typically looks a lot like this. The curve can obviously change based on the number of parameters, but typically the exponential distribution is some curve that ends up looking like this, such that as time goes on, the likelihood something will happen is decreasing. So for instance, when I'm using my exponential distribution as a way to predict how far apart the events will be that have already been described by the Poisson distribution. For instance, two events in a business happening every 10 minutes. The question becomes, how many minutes after the first event will the second one actually happen? It's most likely to occur sooner than later, and the exponential distribution gives me that kind of framework as I go. So this constantly decreasing function in the exponential distribution is very, very useful in a lot of engineering situations, but it's not useful in all situations. There are situations where we're coming up with a lambda or we're estimating our parameters, and the thing we're looking at is something different. In reliability engineering, we often talk in terms of what's called a bathtub curve. It looks about like this. Okay, and the shape can be different. It can be different steepnesses as you come across the model. It can be any number of different shapes. And typically, reliability of this kind of estimate is not going to be governed by the exponential distribution. It's going to be governed by the Weibull distribution. Now, the exponential distribution is, in fact, a subclass of Weibull distributions where alpha is equal to 1. So if I have a Weibull distribution and I have alpha set to 1, I actually have an exponential distribution. But the variation in beta of a Weibull, along with the differences in shape parameter, can have a significant impact on the shape of my curve as I go. The way this basic distribution works, again, is time from the left to the right, but it acknowledges that many products, many services start out with fairly high defect rates. What's known as a burn-in period can happen here, where a lot of things tend to fail fairly early in the life cycle. In healthcare, we call this infant mortality, that once you're born, once you survive to age 5, you're probably going to live a long time, but you're at much higher risk in those early years. So there's a transition point around here where you transition from this steep decline curve for failure rates to something that's more flat as it goes through. Not necessarily absolutely flat, but more flat as it goes through. Likewise, no matter how long a product lives, there's some point out in the future where past that point you can expect the product or service to start to fail fairly dramatically. That's the old age of the product, and eventually it's going to wear out as it goes. So there's really these 3 stages to reliability. This early burn-in period, the general life or the running period that goes on, and the wearing out end life of the product. And this is known as the bathtub curve for obvious reasons based on its shape. Now typically you would describe this with a Weibull distributions or a set of Weibull distributions that would have different alpha and beta. So alpha and beta are the parameters of the Weibull distribution. If I'm on a declining curve like in the early times, typically I'm looking at a beta of less than 1. Typically I've got a beta of about 1, or if not equal to 1 on my flat curve, and then a beta greater than 1 on the far side. The alpha can vary, so my alpha shape determines how steep this is or how much things are stretched or things of that nature. So the alpha is a shape parameter. We don't need it for this discussion. But the distribution of failures over a product can typically be described by a Weibull distribution that is more powerful than just an exponential distribution alone. So although we tend to talk about and practice the exponential distribution, and the exponential distribution is very, very important anytime you're modeling the time period between events that are described by the Poisson distribution, that would exclusively be the exponential. But as you move your exponential distribution into more and more applications as an engineer, you'll start to look at reliability testing, where this more bathtub-shaped curve with different betas for different portions of the life are going on as you see your way through. So typically as an engineer, when you have this kind of curve, we think as an engineer, our job is to move this point out, if you will. Help the product last longer and longer as you go. Make it so that once it's into that flat period, it can last forever. And the reality is we don't want products that last forever. Most businesses would go out of business in bankruptcy if all the products they sold lasted forever, because they would quickly run out of customers. So there's always a need to have a product that can last long enough but not too long. So the challenge between engineering and marketing is we want people to want to buy a new product somewhere along this cycle before the product fails overall. So if we can get a customer to want to buy a new product, say a new cell phone every year or every 2 years, it really doesn't make any difference what happens out here at the end of the life cycle, because they're never going to own the product long enough. So if I can get a cell phone that won't start wearing out until 5 or 10 years, no one will ever know it because nobody uses their cell phone that long. So that blend between marketing, so it helps to engineer the product to last longer, so marketing has the option to go there. And typically my product warranties are something in that time scale as well as I go through. The other thing we do as engineers is try to make sure that there is no burn-in period. Make sure our products are as reliable as possible the moment they're made. So if we're doing our job, our products will be used over the scale that is just this box right here, described by a Weibull distribution with a beta of 1. And we'll have a very reliable, flat, non-distributed reliability curve going on. Our defect rates will be highly predictable and things of that nature. So that's just one of the ways we use some of these point estimates to come up with more realistic data. And again, you can come up with an alpha beta estimate for your Weibull in the same way we've been doing for our lambda on the exponential. So the experiments we do to get those values are a bit more complicated because of the complexity of the curve.